We'll start by looking at R of x here. They already did the factoring for us in this case, which was convenient. And what our job here is to do is to figure out what values of x will cause this to be 0, undefined, positive, and negative. So notice that one difference between this and what we did on Friday in terms of finding solutions to some inequalities is that there's another option here, which is the undefined option. Okay, if we have a polynomial, of course, polynomials are never undefined. Okay, but when we have a rational function, we know that these 2 points are going to be important as well, the points that make this bottom equal 0. Okay, in fact, those are going to be 2 of our split points. So not only are we going to use the x-intercepts as split points, but we're also going to use the discontinuities as well. So what that's going to look like then is to just identify all that stuff first of all. So we would define x equals -3 and x equals 1. Okay, these would be where this function would be undefined. Those are going to be where our asymptotes are. And remember, to find the zeros of a rational function, we need to set the top equal to 0. Okay, so bottom equal to 0 gives us the discontinuities. Okay, top equal to 0 gives us the x-intercepts. So if we set the top equal to 0, we're going to get x equals -1. And therefore, those 3, in this case, will be our split points. Now our work is going to look exactly like what we just did with the polynomials. We're going to take those split points, and we're going to put them on the number line, and we're going to do some testing. And that test, just like it did with a polynomial, okay, that test is going to tell us where this function is greater than 0 and where it's less than 0. Okay, so let's start with -4, let's say. -4 would make a negative on top, and on the bottom we'd have a negative times a negative, which would be a positive. So ultimately it would be a negative divided by a positive. Okay, so therefore in that area we'd be negative. If I do -2, that's going to make a negative on top, and it's going to be a positive times a negative on the bottom, which makes a negative over a negative. Negative divided by negative is positive. If I plug in a 0, I'm going to have positive on top, negative on bottom, which makes negative. And then finally, if I plug in something bigger than 1, like 2, I'm going to have positive, positive, positive. And ultimately, it's going to be positive in that area. So again, just like a polynomial function, okay, that tells me the story for any inequality. Okay, if I wanted greater than, I could say it's between -3 and 1, -1 that is, and then from 1 to infinity. Okay, if I wanted less than, of course, it would be -infinity to -3, and then -1 to 1. Okay. So again, by making that sign chart, it essentially answers all 4 inequalities that I might be asked in this situation. Okay. And as always, we can verify that with a graph. So if we were to graph x plus 1 and x plus 3, x minus 1. And if we look to see if what our analysis gave us was accurate, if you look to the left of -3, the branch is below the x-axis. If you look between -3 and -1, okay, the other asymptote, you can see that it's positive, or excuse me, positive until we get to that -1, I should say, and then negative after. Okay. And then from anything beyond to the right side of the 1, which is to the right side of the asymptote, we have a positive branch. Okay. So our analysis again matches up with our picture just like we expected. Okay. So again, key issue here when dealing with a rational function that's new for us today is that the split points are not only the zeros, but they're also the points that make the bottom equal 0, the discontinuities. Okay, those have to be part of your analysis when you do the number line test. Okay. How about questions so far? Good. Shelley? What's the 0 in the, say it again? Well, anything, what would make it 0, of course, is just the top number that makes the top equal 0. So -1 would be your 0. Undefined would be the 2 discontinuities. And then, of course, the positive and negative is right here on the chart.
Yeah. Okay.
Yeah. Okay. Good. Other questions? Okay, I want to look at, in your book, if you will, look with me on page 261. There is another inequality that's presented there that I want to look at the algebra involved in solving this. You notice that it's a rational inequality similar to the one that we had before. Okay, the biggest difference though is that we have essentially two rational functions that are added together, and we want to know when that's less than 0. So the technique that we're going to use in this case to determine our answer is going to be exactly the same as what we just did, except for we need to essentially put these two together first. Okay, if we put these two together, then our analysis will run the same way as it did in the last problem. So just like any fractions, we're going to need to add these two together. So the common denominator, remember we talked about last week, if we have two things that have completely different denominators like this, that multiplying them together will give us a common denominator. So we're going to go ahead and write x plus 3 times x minus 1. And in doing so, we will have multiplied this one by x minus 1, so we'll do the same thing on top, 5 times x minus 1. Similarly over here, we'd have to multiply by x plus 3. And then from there, we can put that all together and get x plus 3 times x minus 1 on the bottom. And then on the top, I'm going to go ahead and distribute these and combine the like terms to get one expression on the top. So we're going to have 5x and 3x, that makes 8x. And then I got negative 5 and positive 9, should be 4. Negative 5, positive 9 if I distribute and combine like terms. Okay. And now we're at a point where we can use that exact same analysis that we did earlier. Okay. So I'm going to start identifying some points here. I know that negative 3 and positive 1 are going to be points that need to be considered because those are where the bottom equals 0. Okay, I know that when the top equals 0, I'm going to get a 0 for this function. So if I set my 8x plus 4 equal to 0, and then solve that, I'm going to get x equals negative 4/8, which should be negative 1/2. And then as soon as I identify all those split points, I can go ahead and make my number line, just like I did last time, and then do some testing. Once we have the test done, then we should be able to answer this question. Alright, so let's start with our number less than negative 3 here. So if I were to put a negative 4 into this, I would have a negative on top, and I would have a negative times a negative on the bottom. So a negative on top, positive on bottom would give me a negative in that area. Between these two, say negative 1 for instance, negative 1 would give me a negative on top. It would give me positive times negative on the bottom, so it would be a negative on the bottom. So negative over negative would give me positive. Remember, do we really care about what value it is? Okay. Remember, all we care about is the sign. We just want to know, is it positive or negative? I'd put 0 in next, then I'd get a positive on the top, and I would get a negative on the bottom. So it would be negative here in that region. Anything bigger than 1, like 2, would make a positive, 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 and therefore we would get positive in that area. Okay. Questions on the analysis part so far? Yes. Exactly. Yep. So really it's nothing different than what we did on Friday with polynomial functions, except for we have to consider the undefined points to be part of our split points. Okay? So not only are we finding the zeros, but we also have to find those points where we have undefined. Okay? Because those could also, changes in plus and minus can occur at those as well. Okay? So yes, that's exactly right. And then answering the question is no different than what we did as well, because right here is the answer. I mean, we're looking at less than 0. Okay? All we need to do is just identify the parts that are negatives. So for this area over here, negative infinity to negative 3, and then negative 1/2 to 1. And remember, it's less than, it's not less than or equal to, so we wouldn't include any of those zeros or undefined points. Okay? And that would do it. One thing that you have to be a little bit careful on here too, you have to pay attention to, is the fact that if we were to have a less than or equal to, you really don't have to pay attention if it's just a less than or a greater than. But if it's an or equal to here, okay, and let's say this one was where we had undefined, would it make sense to include it even if it was an or equal to? So remember, if -3 is an asymptote, should it be included in the solution set? No. Okay, can you include the 0? Sure, include the 0, but any of the asymptotes should never be included no matter what the sign is like. Okay, so I want to make sure you're careful about that as well. Alright, questions on any part of that one? Again, the key difference here is when we had two separate rational functions, okay, we want to put those together into one fraction first, okay, and then we can run the analysis the same way that we've been doing.